In this video, we'll begin our discussion of section 4.2. What this will be, it will be a second order diffeq, and what we're going to do is turn our second order diffeq into a first order, which will allow us use the methods from last unit to solve. Okay, so the whole idea, let's start here. Suppose that y1 denotes a non-trivial solution to the second order diffeq, and that y1 is defined on an interval I. We seek a second solution y2 so the set consisting of y1 and y2 is linearly independent on I. Okay, so let's start there, and let's just talk about what that means. All right, so if they are linearly dependent, let's start there. Then there's a c1 times y1 plus c2 times y2 equals 0. That's the whole definition of linearly dependent. I know we're not talking about independent yet, but that's okay. So that equation is true. So I can manipulate this thing by moving things around. I'm going to move the second term over. And then I'm going to divide both sides by y2 and divide both sides by c1. So if they are linearly dependent, then I know since that first equation was true, that this expression negative c2 over c1, since those were originally constants, and I know those constants exist, then I know that's a constant the whole time. So y1 divided by y2 will always give me a constant. This makes sense anyway, because dependent means that they are multiples of each other, right? We can create constants. I guess multiples is a, no, it still works, multiples of each other that they can be created from each other. So these constants exist. Well, if they were linearly independent, then I get the same thing, except for it can't be that. There is no C such that's true. So what that means is I will never get this y1 divided by y2 equals some big constant. That's never going to happen. So if it's not a constant, then, right? And a constant can be a crazy decimal, it can be a fraction, it can be a radical, it can be pi, it can be any number. Well, if I know that that's never true, then if they're linearly independent, then their quotient will be a non-constant, right? Think about that. If it's not a constant, right, they don't divide to a number, then that means the x's are still there. There's a function. So using that statement, that I can divide these two functions and I don't get a number, I get a function. Well, I can just take that if that's true, and we can divide or multiply both sides by y1, and we have this new solution. As long as y1 and y2 are linearly independent. So how this is going to work, we are going to make a sub, right here, y equals u times y1. If I make that sub, we'll be able to work all this out to be able to replace to get a first order diffeq. All right, so they gave us y1, so I'm going to go ahead and write y2 here. I guess that should be a y2 up here, my bad. So y2. So y2 prime, or let's go ahead and write y2 first. It's going to be u times x e to the negative x. I grabbed that y1 here. So that means y2 prime, it's going to be a product rule and a product rule. U is a function of x. So uh, we get, let's write it out long ways just in case maybe you need it. All right, so there's our product rule. Derivative of u is u prime, x e to the negative x, and then I'm going to get plus u, and then this is going to be a product rule, so e to the negative x minus x e to the negative x. Right, we could probably reduce that down. I notice everything has an e to the negative x, so let's make our life easier. E to the negative x times u prime x plus u. I actually want to kind of put these in order, so we'll do a minus ux plus u. All right, there's my single prime. Let's go ahead and get our double prime. This is where a lot of this work. We'll probably fill this first little space up with that, unless you're writing much smaller than I am. Actually, I could do this. All right, so there's my y and y prime. Let's get the second one now. So this is a product rule. It's going to be d dx of e to the negative x times u prime x minus ux plus u plus e to the negative x times the derivative. Okay, maybe I should have kept it down there. Wishful thinking. Sorry to annoy you. All right, so I have that. It's just my product rule. All right, derivative, I'm going to get negative e to the negative x times u prime x minus ux plus u. I didn't touch it. Plus e to the negative x. And then these are going to be a couple product rules. I got u double prime x plus u prime. Right, and then the second, that was the first. This is going to be our second quotient rule. I get u minus u prime x plus u prime. They both have neg e to the negative x. So I'm going to go ahead and start factoring. So we got to be careful here. I'm going to factor out an e to the negative x, which means I got to change the signs of the first bit, but that'll allow me just to keep the second bit the way it is. Right. Then we'll combine like terms if they exist. So I see, I'm going to underline or mark out as I go. I have that has nothing. So I'm going to keep that u. We have e to the negative x, and then I have u double prime x. Now I'm going to look for single prime x's. So single prime x, single prime x. Okay, I get two of those. Minus 2u prime x. All right, the next thing we'll underline, I think ux is right here, and that's it. So plus ux. All right, and then plus u prime, 2u prime, and then minus 2u. Right, so there's our second derivative. So it took all that to get that. So now what we're going to do is we're going to do y double prime plus 2y prime plus y. And I'm going to put the 2's in here. Right, that's what we're going to plug in. So I know if I look at these, everything, I'm going to highlight them so I know what to add. I have that. And then this is going to be times 2. And then this is time, that'll be the double derivative. So maybe we should delete that, and I'll go ahead and put 2y2 prime, and we can go ahead and put the 2 through it. That way I don't have to think very hard about it. All right, and then I'm adding this. So all three of those are what are being added. I know all three have an e to the negative x. So I'm going to add the in terms, okay, u double prime x, right? Then I'm looking for u prime x. Well, if you look, cancels with that. Okay, what else happens? Okay, I got ux. This has, I know it's not totally clear, but do you see a ux here, minus 2ux here? They're gone. Right, and then I got a 2u and a minus 2u that are also gone. So the only thing left will be 2u prime equals 0. All right, from here, we can make a pretty big jump. E to the x, this thing, no matter what x you pick, it will never ever be 0. So what that means is that the inside must be 0. Okay, notice that this is a pretty simple second order diffie. So what I'm going to do is I'm going to let w be u prime, and I'm going to let w prime be u double prime. We then, if I make this replacement, I get u prime, or sorry, w prime x plus 2w equals 0. Well, if I move this around a bit, you can see that this is a first order linear equation. So what that means, I'm going to find a mu. Oops. Mu of x is equal to e to the integral of 2 over x dx. Well, that means that's e to the 2 times ln of x. Well, that's e to the ln of x squared, which means this is x squared. So knowing my first order linear, I know d dx. I'm going to have this times my integrating factor times my dependent variable. And I have that. If I take the integral of both sides, I get x squared w times ac. I'm going to call it C1 because these things are going to change a bit. All right, so if I have that, I can also now solve w of x is equal to C1 times x to the negative 2. So there's our function. But remember, we're not solving for w. I got to go back. This is u prime, c1 times x to the negative 2. So to find u of x now, to go backwards, I just integrate. So I get a up by 1, that's negative 1, divided by the new one, that's negative c1 times x to the negative 1 plus a c2. All right, so there's u. We're going to choose always choose c2 to be 0, that second constant. And then the other one, I'm going to put a line here because it doesn't go with always. The other one is c1. I'm going to let that be a negative 1. Usually what we shoot for is for the coefficient to be a 1. What that means then is that u of x is equal to x to the negative 1. So I can come up with y2. Y2 is equal to u times y1. So y2 of x is going to be x, or equals, u is x to the negative 1 times, and then y1 is x, e to the negative x. Well, that leaves me with just e to the negative x. So I know that y2 now, I have that second solution, and this will be an independent, linearly independent solution from y1. We could double check that with the Wronskian if we would like, but there is our y2. This method is a lot of plug and chug. So I know that when I was first going through it as a student, or even going through it prepping for this lesson, my mistakes, at least for me, happened in here. Go slow, make sure all the numbers are right. Don't go quickly through it. My second video for this section will be on the surface, looks simpler, but will be a little longer. So I'll do one more example, and then we're going to do it in the general case, and then we're going to have a formula for this that I'm going to require you guys both to know how to do it and use the formula. So I'll explain that once we get there.